Okay, well, let's take a look at some of the review problems. So certainly in linear algebra, you have to know how to calculate with matrices. So first problem, we have the matrix A and the matrix B, and we multiply them. So AB is this times this. So this looks like 10 minus 6, 25 minus 1, minus 6 plus 66 is 60, minus 15 plus 11. So if I did the arithmetic right, can't guarantee it, but if I did the arithmetic right, that's AB. When you multiply matrices in opposite orders, you don't necessarily get the same matrix. That's very important. So 2, 6, 5, 1, 5 minus 3 minus 1, 11. So I multiply in the order BA, I get 10 minus 15, minus 2 plus 55, 30 minus 3, minus 6 plus 11. And these aren't even close to looking the same. If I subtract them, this is definitely not 0. This is 424, 60 minus 4 minus 553, 27, 5. 4 plus 5 is 9. 24 minus 53 is minus 29, I believe. 60 minus 27 is 33, and minus 4 minus 5 is minus 9. So I don't guarantee that my arithmetic is correct, but that's matrix multiplication. Problem 2 is to show that the inverse of a matrix A is just the matrix if A is invertible. So we always say B is the inverse of A if AB and BA equal the identity. So if A inverse is the inverse of A, that means that A inverse A and A inverse is the identity. So here I have A inverse times A and A times A inverse.
Professor, if you can move that paper up.
That's exactly saying that the inverse of A inverse is equal to A. Okay, any questions about this? Problem 3, we have 4 vectors in 3-dimensional space, R3. And 4 vectors in a 3-dimensional space, R3, must be linearly dependent. So we know, in fact, that there have to exist scalars, x1, x2, x3, x4, such that x1 v1 plus x2 v2 plus x3 v3 plus x4 v4 is the zero vector, and we want to compute them. Compute the scalars, find them. So we have to solve some equations. x1 v1 plus x2 v2 plus x3 plus x4 equals the zero vector. Means if you look at the coordinates, the first coordinate, 2x1 minus 4x2 plus 6x3 plus 10x4 has to be zero. Second coordinate is 2x1 minus 3x2 plus 9x3 plus 21x4, that has to be zero. And the third coordinate, x1 minus x2 plus 8x3 plus 9x4 has to be zero. So we have to solve 3 equations and 4 unknowns. And a heuristic rule is if you have more unknowns, more variables than equations, there's usually a non-trivial solution, a non-zero solution. So one way to do it is just to start to eliminate variables. There are lots of ways to solve equations. Like if I take the second equation minus the first equation, 2x1 minus 2x1 cancels. Minus 3x2 minus this gives me x2. 9 minus 6 is 3. 21 minus 10 is 11. When I eliminate x1 from the first equation, sorry, from these 2 equations, I eliminate x1. If I take this equation minus 2 times this equation, I get 2 minus 2, 0. Minus 3 minus minus 2 is minus x2. Let me just write it out so you see what I'm doing. So this first equation is 2x1 minus 3x2 plus 9x3 plus 21x4 equals 0. If I multiply this equation by 2, 2x1 minus 2x2 plus 16x3 plus 18x4 equals 0. If I subtract, say I subtract this equation from this equation, I get x2, this equation minus this, plus 7x3 minus 3x4 equals 0. See, from these 2 equations.
Yeah, Professor.
Yeah.
Yeah, the x2, isn't it minus? Or
So I'm taking, let's see, this equation minus this equation.
oh, okay, okay.
So I get minus 2 plus 3, 16 minus 9, 18 minus 21. And then if I take, let's say, this equation minus this equation, I get 4x3 minus 12x4 equals 0. Or if I divide by 4, x3 minus 3x4 equals 0. So it says like x3 should be equal to 3x4. So let's just see if I can use that and work my way back. So I have x3 equals 3x4. So maybe let x4 equal 1. And then x3 would be 3. And they say from this equation, x2 plus 7x3 minus 3x4 is 0. So x2 is minus 7x3 plus 3x4. So that's minus 7 times 3 plus 3 times 1. That's minus 21 plus 3 is minus 18. And then from this equation, I get x1 is x2 minus 8x3 minus 9x4. I don't believe I'm not making some arithmetic mistakes, but we'll see in the end. So that's x2 is minus 18 minus 8x3, that's minus 24, minus 9x4 minus 9. So this is minus 18 minus 24 is minus 42 minus 51. So let's just see what happens when I look at this linear combination. I get x1 v1 plus x2 v2 plus x3 v3 plus x4 v4. So that's minus 51, 221, minus 18, minus 4, minus 3, 1, minus 4, minus 3, minus 1, plus 3x3, 698, plus 4x v4, which is 10, 21, 9. So that's equal to minus 102, minus 102, 51, plus 72, 54, 18, plus 18, 27, 24, plus 10, 21, 9. So, yeah, so something's wrong, of course. This is 90, this is 100, and this is 102. So close doesn't count. This is 48 and 54, that is 102. This is completely, oh, this should be minus 51 certainly. So this is 18 and 24 is 42, 51. So this is 0, 0, but I didn't get 0 here. Let's see, what did I do wrong? Minus 102 plus 72 plus 18 plus 10. Close, but no cigar. Let me just run through this quickly and see where I might have made a mistake. So the vectors are 2, 2, 1, minus 4, minus 3, minus 1, 6, 9, 8, 10, 21, 9. 2x1 minus 4x2, 6x3, 10x4, 2x1 minus 3x2 plus 9x3 plus 21x4, x1 minus x2, 8x3, 9x4. So when I subtract these two equations, I get x2 plus 3x3 plus 11x4. That seems okay. When I take this equation, 2 minus 3, 9, 21, multiply this by 2, 2 minus 2, 16, 18, and I subtract, I get x2, 7 minus 3. And then when I subtract these equations, I get 4x3 minus 12x4. So x3 equals 3x4. So if x4 is 1, x3 would be 3. And then x2 plus 7 minus 3. X2 is minus 7x3 plus 3x4. So this would be minus 21 plus 3 is minus 18. And x1 is x2 minus 8x3 minus 9x4. So that's minus 18 minus 24 minus 9. So that's minus 33, 43, 51, minus 51. So x1 times v1 is minus 51 times 221. x2 v2 is minus 18. So this becomes plus 36, 54, 18. Plus 3 times 698, 698, plus 10, 21, 9. So I cannot see where I made my mistake. That should be a 0 there. All right, oh, I don't want to spend more time on it now, but in any case, this is just one method that if you do it correctly and don't avoid arithmetical errors, will definitely give you the linear combination of the vectors that's equal to 0. Okay. Too bad for me. Problem 4, v1, v2, linearly independent vectors, we're given that. Show that if I take a certain linear combination of the vectors, v1 plus 2v2 and 3, 1 minus v2, so these are linearly independent. So suppose x1 times v1 plus 2v2 plus x2 times 3, 1 minus v2 is 0. To show they're independent, I must show x1 equals x2 equals 0. So this is x1 v1 plus 2x1 v2 plus 3x2 v1 minus x2 v2 equals 0. Or this is x1 plus 3x2 v1 plus 2x1 minus x2 v2 equals 0. But we know v1 and v2 are linearly independent. That's what we're given. So x1 plus 3x2 has to equal 0, and 2x1 minus x2 equals 0. So we have to solve two equations and two unknowns. This simply says that x2 is 2x1. So x1 plus 3x2 is x1 plus 3 times 2x1, which is 7 times x1 is 0. So x1 is 0. So x2 is 0. So we're done. The only linear combination of these two vectors, which is 0, is the trivial linear combination in which the coefficients are all 0. Okay. That's
Nice
what I'm
one.
for. Thank you. Problem 5, we have V is a vector space. Wi is a subspace of V for all I in some set, capital I. Like if this were like I were the numbers 1, 2, 3, you'd have subspaces W1, W2, and W3. And suppose for all ij in the set I, there exists a k in the set I such that Wi plus Wj, that's the sum of these two subspaces. This is all vectors that you can write as the sum of a vector in Wi plus a vector in Wj. This is contained in Wk. Then we want to show, we have to prove that if I take the union of all these subspaces is a subspace. So of course, let's call this W. So for all I, the vector 0 is in Wi, which is contained in W. So W contains 0. And all we have to do is show that W is closed under vector addition and scalar multiplication. So that V and W be any vectors in W. Or let's say U and V. U and V. Any vectors in W. Which is the union of all these subspaces. So that means there exist subscripts I and J in I such that U is in Wi and V is in some Wj. But there exists some K in the set I with Wi plus Wj contained in Wk. And U plus V, U is in this set, V is in this subspace, U plus V is in this plus this, which is contained in Wk, which is contained in W. So that proves that W is closed under vector addition. That's straightforward. Similarly, if V is in W, then V, the vector V is in some subspace Wi. If I take any scalar C times V, this is in Wi, because Wi is a subspace. So it's closed under scalar multiplication. And that's certainly contained in W. So if V is in W, every scalar times V is in W. And that's a proof that W is a subspace. Okay. Any questions about that? Let's look at problem 6. So we have a set W1, W2 up to W sub M of M vectors contained in V, which is some vector space. And suppose we let W be the subspace of V generated by the set X. So W consists of all linear combinations of vectors in S. So the subspace W is everything you can write in the form x1 W1 plus x2 W2 plus x sub m Wm, where these xi's run through all possible real numbers, or whatever your scalars are. It's any subspace that contains W1 up to Wm contains a linear combination of every linear combination of it. And the set of all linear combinations is in fact a subspace. Suppose we take a set of V1, V2, V sub n. These are n distinct vectors in W, where n is bigger than m. So W is a subspace generated by m elements, and I choose n vectors more than m. Prove that this set, V1, V2, up to V sub n of n vectors, is linearly dependent. So how should we do that? For example, this is like saying if you have a two-dimensional vector space, any three vectors have to be linearly independent. And so let me give you two proofs. So first proof. There is a linearly independent subset of S that generates the subspace W. Because here I have m vectors that generate W. If they're linearly independent, that's a linearly independent set that generates W. If they're not linearly independent, say W sub m is a linear combination of the first m minus 1 vectors, you can replace Wm by a linear combination of the first m minus 1 vectors. And we have a smaller set that generates W. And if that's not linearly independent, you can throw out one of those vectors. And you can continue step by step. So you find a linearly independent subset of S that generates W. Therefore, the dimension of W, let's say it has dimension D, it's at most M. This is M minus whatever vectors you throw out. And in a vector space of dimension D, every linearly independent set contains at most D vectors. And N is bigger than M is greater than or equal to D. So N is bigger than D, so it can't be linearly independent. So that's the key. The dimension of the subspace W is at most M. So any set with more than M vectors must be linearly dependent. let's see if we can give another proof that doesn't use this. Okay. So we have V1 up to Vn are vectors in W, which is generated by the set S. So for example, V1 is some linear combination. Let me scale it. A11 W1 plus A1M WM. And V2 is A21 W1 up to A2M WM up to V sub n, which is A N1 W1 up to A NN WM. And we want to solve the equations x1 v1 up to xn vn equals 0. Can we find non-zero x's that solve this equation? So we have x1 v1 plus x2 v2 up to xn vn. What is that? That's x1 times this, a11 w1 up to a1m wm plus x2 a21 w1 up to a2m wm all the way up to xn vn, which is xn an1 w1 up to anm wm. Let's see. What is the coefficient of W1 in this? We have A11 x1 plus A12 x2 up to A1n xn times W1 equals 0, times W1. And we have a coefficient of W2. This would be, see, this would be A12 W2, would be A12 x1 up to AN2 xn Wn. And then you get a linear combination of W1 up to W sub m. Let's see, I have A1M x1 up to AN M xn. And if I have all these coefficients equal to 0, where all the x's are not 0, I have a linear combination of the v's, a non-trivial linear combination of the v's equal to 0. But what I have here, if I look at this, the coefficient of W1, means I want to solve the equation A11 x1 plus A12 x2 up to A1n xn equals 0. I have m equations. The last equation is A1m x1 up to amn xn equals 0. I have m equations, n variables, and m is less than n. And whenever you have a system of linear equations with more variables than equations, there's always a non-trivial solution. So this gives you a second, completely different proof of this result. And there are other ways to do it as well. It's a very important fact. Any questions about this? Okay. After 6 comes problem 7. So we have a vector space V, and inside V, subspace W1, and W1 is contained in a larger subspace, W2. And we're told the dimension of W1 is K1, the dimension of W2 is K2. So there exist vectors W1 up to WK sub 1. That's the basis for W1. And if W2 is different from W1, then there exists a vector W sub K sub 1 plus 1 in W2 that's not in W1. And if I take this larger set of vectors, W1, W2, WK sub 1, and then I add this new vector, this is again a linearly independent set. Because if there were a dependence relation, the coefficient of WK sub 1 plus 1 couldn't be 0, or otherwise it would be in W1. It's not. And one by one, we can add vectors to vectors in W2 to the basis for W1. So eventually we get some set of vectors that's the basis for W2. So this goes back to the linear algebra we were talking about at the beginning of the semester. You have a subspace of a vector space. You have a subspace of a vector space. You can always, and a larger subspace, you can always extend the basis to the larger subspace. That's all this says. Look at problem 8. We have a basis for R3 where V1 is the vector 1, 1, 0. V2 is the vector 1, 0, 1. V3 is the vector 0, 1, 1. And because it's a basis for R3, every vector is a linear combination of these vectors. So for example, if I take the vector 3 minus 1, 2, I can write that as some x v1 plus y v2 plus z v3. And I want to find the x, y, and z, the coordinates. So this means x times 1, 1, 0 plus y times 1, 0, 1 plus z times 0, 1, 1. This is x plus y, x plus z, y plus z. So we want to solve the equations x plus y equals 3, x plus z equals minus 1, y plus z equals 2. So we're solving 3 equations and 3 unknowns. For example, if I subtract the second equation from the first equation, I get y minus z equals 4. The third equation is y plus z equals 2. If I add, I get 2y equals 6. So y equals 3. If y equals 3, 3 plus z equals 2. So z equals minus 1. X plus y equals 3. Y is 3. So x is 0. So if this is correct, let's just check. X v1 plus y v2 plus z v3 is 0 times 1, 1, 0 plus 3 times 1, 0, 1 plus y times 1, 0 plus z, which is minus 1, 0, 1, 1. So this is wrong. Not a lot. Good day for me. Let's see. 1, 1, 0, 1, 0, 1, 0, 1, 1. So this is x plus y is 3. X plus z is minus 1. Y plus z is 2. Subtracting this minus this, y minus z is 4. Y plus z is 2. 2y is 6, so y is 3. If y is 3, z is minus 1. If y is 3, x is 0. So let's see, what is this? Oh no, maybe this is right. This is 3 minus 1, 2. It does check. Okay, so I actually did the arithmetic right this time. So that is the solution to problem 8. Any questions about this? Okay. 8 is followed by 9. So in problem 9.
I have a question not relating to this problem. You didn't post online when the office hours for this week are going to be?
Oh, as soon as class ends, I'll post them. There'll be office hours. Certainly, I have one office hour that I have scheduled for this evening. It's 7 o'clock, I think. And then I have office hours Thursday and Friday. And I'm also going to have some office hours on the weekend, since the exam is next week. But I'll post it as soon as class is over.
All right, thank you. Sorry about that.
Sure. Okay. So problem 9, we have a matrix, 1, 2, 3, 4, and a linear transformation defined by that matrix from R2 to R2, where T sub A of the vector xy, it's the matrix A times xy, which is 1, 2, 3, 4 times xy. So TA of xy is equal to the vector x plus 2y, 3x plus 4y. So to find the kernel, the vectors in the kernel, if and only if x plus 2y, 3x plus 4y is 0, which means x plus 2y is 0, and 3x plus 4y is 0. So we have to see what are the solutions of these two equations and two unknowns. So for example, if we multiply the first equation, so here I multiply the first equation by 3x plus 6y equals 0. The second equation is this, subtract 2y is 0, so y is 0, so x is 0. So in fact, the kernel the only vector in this kernel is the 0 vector. So the kernel is just 0, and the nullity of this linear transformation is just the dimension of the kernel is 0. And one of the basic theorems in linear algebra is when you have a linear transformation from any vector space to another, the dimension of the kernel plus the dimension of the image is the dimension of your vector space V. So in this case, V equal W, they're both R2. They have dimension 2. So the dimension of the kernel is 0, plus the dimension of the image, I don't know what that is for a minute, is the dimension of R2, which is 2. So the dimension of the image of T is 2. So here we have R2. I had this map, and in here is the image of this linear transformation. But its dimension is 2 in the vector space of 2 dimensions. So that means they have to be equal. So the image of T is R2. So just from using that fundamental theorem, we can see that, that's one way at least, we can see that the image of this linear transformation is all of R2. Because the image is 2-dimensional, and the only, in general, if you have an n-dimensional subspace of an n-dimensional vector space, your subspace is equal to the whole space. You could also prove directly so this linear transformation, TUA of xy, is x plus 2y, 3x plus 4y. And you could ask, well, for what vectors, when is this equal to some vector AB in R2? So the vector AB is in the image of this linear transformation. That's just the definition. That's what it means to be in the image. There's some vector xy, such that T of xy is the vector AB. So you want to know, when can you solve the equations x plus 2y equal A, 3x plus 4y equal B? And these equations have a solution, in fact, a unique solution for all A vectors A, B, and R2. So that would give you, without using the theorem, that would give you a second proof that the image of the linear map is R2. And so the rank of T, which is by definition the dimension of the image, is 2. It's the dimension of R2, which is 2. Any questions about that? All right. Let's look at problem 10. So T from V to W is a linear transformation. Prove that if the set V1, V2 up to V sub K is linearly dependent in V, that implies that their images, T of V1 up to T of VK, that set is linearly dependent in W. And the proof is as follows. If V1 up to Vk are linearly dependent, there exist scalars x1 up to xk, not all zero, such that x1 v1 plus x2 v2 up to x sub k v sub k is zero. Therefore, t of zero, which is zero, right? The linear map always sends the zero vector to the zero vector, t of zero, but this is a way to write zero. T of zero, this is t of x1 v1 up to xk vk. But then using the linearity of this function t, this is x1 t of v1 and so forth up to x sub k t of vk. So this is a linear combination of t of v1 up to t of vk with scalars, coefficients, these numbers up to x1 up to xk, which are not all zero. So this is a linear dependence relation. So that means that t of v1 up to t of vk, these k vectors, are linearly dependent also. They're not independent. Questions about that? Okay. Let's look at problem number 11. So we have a linear map from R2 to R2 is defined as follows. T of xy is 5x minus y, 3x plus 2y. So in general, so this is the general theory. If you have T from a vector space V to itself, and V has some basis, let's say V1 up to Vn, so T of each basis vector, T of V sub j, is it's in V. So T of Vj is some linear combination of these n vectors, V1 up to Vn. And the matrix for T with respect to this basis, I'll call it B, these coefficients become the column vectors, A11, A21 down to AN1. The jth column vector, A1j, A2j down to ANJ. A1n, A2n down to AN. So this n by n matrix, this is the matrix for this linear transformation with respect to the basis. So we have three different bases to play with in this problem. In part A, we take the standard basis, E, where the vectors in the basis are 1, 0, and 0, 1. So T of 1, 0 is 5, 3. T of 0, 1 is minus 1, 2, So the matrix for T with respect to this basis is 5, 3 minus 1, 2. Part B, we have a different basis. B1 is the basis 11, 0 and 0, 7. So what is T of 11, 0? So when X is 11 and Y is 0, you get 55, 33. But I have to write this as some linear combination of these two basis vectors. And that means this is 11A11, 7A21. So 11A11 equals 55. And 11 and 7A21 equals 33. So A11 is 11 and A21 is 33 over 7. So in this matrix that I'm going to end up with, this is 11 and 33 over 7. Oops, 5. Let me do this correctly.
Professor, can you move the paper down a little bit?
So in my second basis, the basis vectors are 11, 0 and 0, 7. So T applied to the first basis vector, 11, 0, is 5, 55, 33. And I want to write that as a linear combination of these two basis vectors. A11, 11, 0, A21, 0, 7. That's 11, A11, 7, A21. And that has to equal 55, 33. So A11 is equal to 5. And A21 is 33 over 7. When I calculate this for the second basis vector, T of 0, 7, when X is 0 and Y is 7, I get minus 7 over 14. And I need to write this as some linear combination of 11, 0 and 0, 7. This says 7 times A22 is 14. So this coefficient is 2. 11 times this is minus 7. So this coefficient is minus 7 over 11. So the basis, the matrix for this linear transformation with respect to this basis is given by this. Any questions about this? So let me do the third basis. That's more interesting. So this is problem 11C. We have T of xy is 5x minus 2y, 3x, so 5x minus y, (3x plus 2y), and I have a basis B2 consisting of the vectors 1, 1 and minus 1, 1. Let me call this W1, W2. So T of W1, that's T of the vector 1, 1. When X and Y are 1, this is 5 minus 1 or 4, 3 plus 2 or 5. And then I want to write that as a linear combination of my two basis vectors. So A11 W1 plus A21 W2. That means A11 times the vector 1, 1 plus A21 times the vector minus 1, 1. This is the vector A11 minus A21. This is a plus. A11 plus A21. So I have to solve the equations. A11 minus A21 equals 4. A11 plus A21 equals 5. When I add, these cancel. I get 2A11 equals 9. So A11 is 9 halves. And A11 plus A21 is 5. So A21, this is 4.5 plus a half gives 5. 4.5 minus a half gives 4. So that's going to give me the first column of my matrix. So T with respect to the matrix B2, the first column is going to be 9 halves, 1 half. What about the second basis vector? T of W2, that's T of the vector minus 1, 1. When X is minus 1 and Y is plus 1, I get minus 6. Minus 1 plus 1, minus 3, I get minus 6 minus 1. And I have to write that as a linear combination of these two vectors. A 1, 2, 1, 1 plus a 2, 2 minus 1, 1. That's a 1, 2 minus a 2, 2, a 1, 2 plus a 2, 2. So I have, again, these two equations and two unknowns to solve. A1, 2 minus A2, 2 equals minus 6. A1, 2 plus A2, 2 equals minus 1. When I add, I get 2A1, 2 is minus 7. A1, 2 is minus 3 halves. So A2, 2 has to be, oops, A1, 2, 2A12 is minus 7, so A12 is minus 7 halves, and A22 is minus 5 halves. Is that right? A12 plus A22 is minus 1. So plus 5 halves. Of course, then A12 plus A22 is minus 1, and this minus this is minus 6. So we get minus 7 halves, 5 halves. And that's the matrix for this linear transformation with respect to the basis B2. All right, any questions? Questions about this? All right. This was question 11, so next must be question 12. So V is an inner product space. W is a subspace of V. And suppose a script B, which is W1 up to WK, is a basis for W. So W perp is the set of all vectors V and V such that the inner product of V and W is 0. So in particular, if your basis vector Wi is in W for all I, so V inner product with Wi is 0 for all I. Conversely, if the inner product of V and Wi is 0 for all I, then you say any vector V in the vector space V so suppose you have a vector in V and its inner product with every one of these basis vectors is 0, let W be in W. So then this vector W is some linear combination of the vectors in the basis for W. And if you use the bilinearity of the inner product of V and W is the inner product of V with summation xi Wi. I goes from 1 up to k, because I can write the vector W as a linear combination of the basis vectors. But using bilinearity, this is summation. I goes from 1 to k, x of I, v w I. And each of these is 0. And the sum of zeros is 0. So a vector is in the orthogonal complement of the subspace W if and only if it's perpendicular to every vector in the basis for W. So that's problem 12. Any questions so far? No. 12 must be followed by 13. So we have a linear operator from the vector space to itself, and lambda 1 up to lambda k are distinct eigenvalues. So every eigenvalue has an eigenvector. The v1 up to vk be non-zero vectors such that p of the vector vi is the eigenvalue lambda I times vi for all I from 1 up to k. We want to show v1 up to vk is a linearly independent set. So let's say I'll do it with proof. By induction on k. K equals 1, it's very simple. V1 is non-zero, so the set V1 is linearly independent. Every set consisting of just one non-zero vector It's linearly independent. What about K2? So suppose we have P of V1 is lambda 1 V1. P of V2 is lambda 2 V2. And lambda 1 are distinct eigenvalues. And V1 and V2 are non-zero vectors. So suppose x1 V1 plus x2 V2 is 0. Suppose some linear combination of V1 and V2 is 0 must prove x1 and x2 are both 0. That will prove the linear independence of these two eigenvectors. Well, if this is 0, then T of x1 V1 plus x2 V2 is T of 0, which is the 0 vector. But of course, 0, that's T of x1 V1 plus x2 V2. Using the fact that T is a linear operator, this is x1 T of V1 plus x2 T of V2. But T of V1, V1 is an eigenvector for the eigenvalue lambda. This is lambda 1 x1 V1. And this is T of V2 is lambda 2 V2. I get lambda 2 x2 V2. So now I have two vector equations. I have lambda 1 x1 V1 plus lambda 2 x2 V2 is 0. And x1 V1 plus x2 V2 is 0. Multiply the second equation by lambda 1. And lambda 1 x1 V1 plus lambda 2 x2 V2 equals 0. If I multiply this equation by lambda 1, I get lambda 1 x1 V1 plus lambda 1 x2 V2 equals 0. And now subtract this minus this. These cancel. So I get lambda 2 x2 V2 minus lambda 1 x2 V2 equals 0. But this is a scalar, lambda 1, sorry, this is lambda 2 minus lambda 1 x2 times V2. I can factor out it's lambda 2 x2 minus lambda 1 x2, which is lambda 2 minus lambda 1 times x2 V2 equals 0. So lambda 2 minus lambda 1 x2 is 0. But lambda 1 is different from lambda 2. So lambda 2 minus lambda 1 is non-zero. So if the product of two numbers is 0 and one of them is not 0, x2 is 0. And if x2 is 0, x1 is 0. And we're done. So that's the case for 2. And so let's assume true for n, at least 2 eigenvalues. And now, let lambda 1, lambda n plus 1 be n plus 1 distinct eigenvalues with v1 up to v sub n plus 1 eigenvectors. So suppose I have a linear combination x1 v1 up to xn vn plus xn plus 1 vn plus 1 equal to 0. Now we know by induction that v1 up to vn are linearly independent. But our induction hypothesis is that eigenvectors corresponding to any n distinct eigenvalues are linearly independent. Now I want to consider the case with n plus 1. So if I apply t to this vector, that's t of 0, which is 0. And then using the linearity of t, I get that t of x1, v1. Let me just write this out in steps. X1, v1. Xn, vn. Xn plus 1. Vn plus 1. That's t of x1, v1 plus t of xn, vn plus t of xn plus 1, vn plus 1. Then I can take the scalars outside, x1 t of v1, xn t of vn, xn plus 1 t of vn plus 1. But the v's are eigenvalues, eigenvectors. T of vi is lambda I vi. So this is x1 lambda 1 v1 to xn lambda n vn plus xn plus 1 lambda n plus 1 vn plus 1, all equal to the 0 vector. And we started off with a linear combination x1 v1 xn vn xn plus 1 vn plus 1 equal to the 0 vector. Multiply this last equation by lambda n plus 1. So I have two equations and these two terms are the same. So if I subtract, they cancel. What I get is lambda 1 minus lambda n plus 1 x1 v1 up to lambda n minus lambda n plus 1 xn vn equals 0. So this is a linear combination of v1 up to vn. And those vectors are independent. So each one of these coefficients, lambda I minus lambda n plus 1 xi, is 0 for I going from 1 up to n. And lambda I is different from lambda n plus 1 because we have distinct eigenvalues. So xi is 0 for I going from 1 up to n. And that means that xn plus 1 vn plus 1 is 0. So xn plus 1 is 0. So that proves linear independence. If you have distinct eigenvalues, the set of any set of eigenvectors corresponding to those eigenvalues is linearly independent. Any questions about that? All right, we have a little bit more time, so I'll try one more problem. Number 14. We have the matrix 4 minus 2, 7, 5. 7 minus 5. 4 minus 2, 7 minus 5. So we want to compute eigenvalues and eigenvectors. So lambda is in the spectrum of A, that's an eigenvalue. If there's a vector such that 4 minus 2, 7 minus 5 applied to the vector xy is lambda times xy. We want a non-zero vector. This says 4x plus 7y. This is minus 2x minus 5y equals lambda x lambda y. So we're solving two equations and two unknowns. 4x plus 7y equals lambda x minus 2x minus 5y equals lambda y. And if I move everything over to the right side of the equation, I get lambda minus 4x minus 7y equals 0. And 2x plus lambda plus 5y equals 0. And this has a non-trivial solution for lambda if the determinant of the coefficients, I mean, you can also just solve it, but the determinant of the coefficients, which is lambda minus 4, lambda plus 5, minus 2 times minus 7 is 0. See, this says lambda squared plus lambda minus 20 plus 14 is minus 6 equals 0. And this quadratic factors, that's correct. This is lambda plus 3, lambda minus 2. So the spectrum, the eigenvalues are 2 and minus 3. So let's see if we can find the eigenvectors. So here are the equations we have to solve. Let's say for lambda equal 2. Put it this way, lambda is equal to 2. It says 2 minus 4 minus 2x minus 7y equals 0. And this is 2x plus 7y equals 0. So y is minus 2 over 7. That's one solution. And x, or let's make it easier. I could let just x equals 7, y equals minus 2. X equals 7, y equals minus 2, certainly works. So the vector 7 minus 2 is an eigenvector corresponding to the eigenvalue lambda equal 2. And if I let lambda equal negative 3, this equation, for example, is 2x plus 2y equals 0, so y equals minus x. So I could take the vector v equal to x equal 1, y equals minus 1, the lambda equal minus 3. And you can check that this is indeed an eigenvector with eigenvalue 2, and this is an eigenvector with eigenvalue negative 3. Okay. Any questions about any of this so far? All right. Well, I'm going to stop at this point. We will have office hours basically every day until the final, I think. But if you need to talk to me and you can't make one of the office hours, then send me an email and I'll try and set up a mutually convenient time. Okay.
Excuse me, Professor.
Yes, sir.
I have a question, not necessarily pertaining to this class. I saw that you were teaching math 226 for vector calculus, and it says it's hybrid for the fall semester. Does that mean that like we're gonna be in person, or is it like kind of like this class where it's online mostly?
I think it's going to be like this class and basically online.
Okay, I just wanted to confirm.
Sure. Other questions?
Not about, I guess, this lesson or anything. I haven't gotten a grade back for my midterm. You're still grading them, or?
The second midterm?
Yeah.
Yeah, I said at the beginning, I've graded about half of them and I'll have the rest graded by tomorrow morning.
All right. Also, I'll be handing in any last minute assignments by tomorrow, ideally.
That's fine. I mean, at this point, if you just get them in by the final exam date, I'll count them just as well.
All right. Thank you.
Okay.
Professor,
Yes, sir.
what time do you have your office hours?
What time do I have my office hours?
Yes.
Oh, I said that I'll have one at 7 o'clock tonight, but as soon as the class is over and I get the video posted, I'll send out an email with all my office hours for the next week.
Okay.